All right, welcome to this explainer brought to you by Forge College. Today, we're putting on our trench coats, grabbing our magnifying glasses, and becoming full-blown detectives. And we're not just tracking down any ordinary suspects. No, we are hunting the absolute most elusive, chaotic, non-deterministic bugs in Solana programming. Now, if you've been following our track on programming with Solana, and specifically the Advanced Solana Program Structures module, you know we've been getting into some heavy stuff. In our last lesson, we covered applying ownership and memory principles to safe Rust code. But Today we are talking about debugging concurrency and unsafe patterns. This is where things get a little weird, a little chaotic, and honestly highly unpredictable if you aren't super careful. So get comfortable and let's get into it. We have a very strict investigation roadmap to follow today. We'll start with the illusion of safety, move on to meet the suspects, setting the trap, exploring our forensic tools, locking down the fix, and finally, your final debug report.
Okay, Section 1, the illusion of safety, exploring safe versus unsafe Rust.
So up until now, we've basically been living in this wonderful, safe little bubble, right? We've been applying strict ownership rules to keep our data completely secure. But the second we step out of that bubble, the rules of the game change completely. Think of safe Rust like having the world's strictest bouncer at the door of an exclusive club. The compiler checks ownership, it enforces strict borrowing rules, and it makes absolutely sure that your memory doesn't get messed with at compile time. It's safe. But then we have unsafe Rust. Unsafe code acts like a backdoor. You're basically whispering to that strict bouncer, hey, don't worry about me, I know exactly what I'm doing. But the massive problem here is that if you don't actually know what you're doing, you leave your program completely vulnerable to runtime chaos. Things like raw pointers and concurrent threads, they just bypass those compiler safety nets entirely. So even code that compiles perfectly can exhibit data races or undefined behavior once it's actually running out in the wild, especially in highly resource-constrained environments, like a Solana program.
Moving on to Section 2, let's meet the suspects, our most common memory bugs.
It is time to profile the two most wanted criminals in the Solana ecosystem. Our first slippery suspect is the data race. Imagine two people trying to write a completely different sentence on the exact same spot on a whiteboard at the exact same time, without even looking at each other. It's going to be unreadable garbage, right? Well, that's exactly what a data race is. It's a bug that strikes when multiple threads mutate the exact same data without any synchronization. In a local testing environment, or maybe with worker threads off-chain, this leads to incredibly unpredictable behavior, where your program's state just gets entirely scrambled. And the craziest part? It compiles perfectly fine. Because raw pointers implement the send trait, the compiler thinks everything is cool. But at runtime, absolute disaster. And our second culprit is the notorious use after free bug. This is essentially an aliasing violation. Think of it kind of like holding onto the keys to a house, but after the house has been entirely demolished and replaced by a bank. If you walk up and try to open the front door with those old keys, you're going to end up in a very confusing, undefined situation. In code, this happens when a rogue pointer outlives its owner and tries to access empty or reallocated space. Because we used an unsafe block to bypass the borrow checker, the poor compiler literally couldn't warn us that the underlying data was already gone.
All right, Section 3, setting the trap and reproducing the bug.
To actually catch these non-deterministic criminals, we need to set up a highly controlled crime scene. By intentionally bypassing safety checks and spawning threads, we create a minimal, reproducible test case to basically bait the bug out of hiding. Here is how we do it. Step 1, we add a dev dependency called loom to our project. Step 2, we write a deliberately unsafe helper function in our library. We'll call it make_raw_shared. What this function does is allocate a boxed integer and then purposefully leaks it as a raw pointer. We are literally throwing away the ownership rules on purpose. Then, step 3, we write a test that spawns two unsynchronized threads that both try to write to that exact same raw pointer. When you run a standard cargo test on this, it might pass sometimes, and it might fail other times. It is completely non-deterministic. But you know what? That is exactly the chaotic behavior we are trying to isolate.
Which brings us to Section 4, forensic tools. Let's look at Miri and Loom.
Let's crack open our toolkit and gather some rock-solid forensic evidence. The crucial point here is understanding exactly which tool does what. Loom is basically our time-manipulating detective. See, normal tests might completely miss a data race just because the threads happen to execute in a safe order by sheer luck, but Loom,
Loom systematically explores every single possible multi-thread interleaving. It forces the chaotic timelines to play out one by one until it deterministically finds the exact sequence that causes the crash. On the other hand, we have Miri. Miri acts as our microscope for pinpointing microscopic memory violations. It detects undefined behavior, things like invalid reads, invalid writes, and our old friend, the use after free bug, even in a completely single-threaded context. So, rule of thumb. If Loom finds a crash, but Miri doesn't flag undefined behavior, you've very likely got a concurrency data race. But if Miri flags undefined behavior right away, you've got an aliasing or pointer issue on your hands.
Section 5. Locking down the fix using sync primitives.
Okay, once we have isolated the root cause, it is time to lock the culprits away so they can't cause any more damage. To do this, you need a solid blueprint for choosing the exact high-level synchronization primitive to secure your memory. If you have a data race, you absolutely need to synchronize. If you need exclusive mutable access across your threads, you use a mutex. It's straightforward, it's safe, though keep in mind it can cause some blocking. Now, if you have a situation where you have many readers but very few writers, you might want to opt for an RW lock to get higher read parallelism. For simple numeric flags or counters, atomic types offer really low overhead without any of the heavy locking. And finally, if you are building your own low-level primitives from scratch and you need interior mutability, you use UnsafeCell. But I have to warn you, that gives you highly granular control at the steep cost of having to manually enforce all the safety invariants yourself. The big takeaway here, always prefer these safe high-level wrappers over trying to write your own ad hoc unsafe fixes.
And finally, Section 6, your final debug report, the actionable paperwork. Look, every good investigation ends with paperwork, and this paperwork serves as the absolute foundation for your future architectural decisions. To close out a bug ticket properly, your final debug report has to be concise, and it has to be actionable. First, clearly document the reproduction steps. How exactly did you trigger this chaotic behavior? Second, paste in the actual forensic tool outputs, the specific error traces from Loom or Miri. Third, write a one-paragraph root cause analysis that ties the failure directly back to ownership, aliasing rules, or unsynchronized access. And lastly, include a deterministically tested patch that proves you've restored memory safety using one of those primitives we just talked about. This artifact is crucial because it proves you didn't just guess the fix, you actually engineered it. If you take away literally anything from this entire investigation, please remember this golden rule. Compilation success does not imply runtime safety. I'm going to say that again. Compilation success does not imply runtime safety. When you open that unsafe backdoor, a green light from the Rust compiler means absolutely nothing if your underlying logic is flawed. You have intentionally taken the responsibility away from the compiler and you have placed it squarely onto your own shoulders.
So, take a hard look at your own code. Are your advanced data structures truly safe? Or are you just getting incredibly lucky with how your threads happen to be scheduling? As we prepare for our next lesson in this module, which covers implementing high-performance data structures safely, I'll leave you to ponder that provocative thought. Thank you so much for joining me for this explainer. If you want to dive even deeper into advanced Rust concepts for Solana, or if you want to check out our full programming with Solana track, be sure to visit forge.college for more amazing Web3 resources. See you next time.